Hello everyone, my name is Zhenlin Lin and I'm the presenter today. Before we dive into the paper, I would like to start with a little story. Imagine you are going out for dinner with a friend and you have promised to pay. Before you leave the house, you think, I'll bring 100 euros, that should be enough. You confidently walk out the door, see the empty beer can you left there yesterday, and suddenly think, oh wait, is 100 euros really enough? We are both alcoholic. What if we end up spending another 100 euros just on alcohol? So you engage in a bit of self reflection. You realize that bringing only 100 euros doesn't make any sense. You go back home, grab a big handful of cash, stuff it into your wallet, and head out again. Self reflection is the first keyword for today. You and your friend eat and drink a lot later at the restaurant, and then it's time to pay. You reach into your pocket confidently and realize, oh no, where's my wallet? My wallet's gone. But you still remember that you still have it when you got out on the train at the station. You and your friend are not excited about staying behind to wash dishes and mop the floor. So you start reconstructing your entire journey from the station to the restaurant. You draw a timeline of what happened, and you and your friend reason about where the wallet might have fallen out. This timeline is the second keyword in this story, and actually in our paper. So if you think about it, what you and your friends are doing right now is exactly learning to reason over time. That brings us to today's paper, Learning to Reason Over Time. Timeline self-reflection for improved temporal reasoning in language models. If you could formalize what you just did, real, turn it into a strategy and feed it to an LLM, and congratulations, you might be able to publish an ACL paper. And ACL is it's like a top tier conference, so maybe washing those dishes would be worth it. So the key to avoiding dishwashing is that in that story is what we called temporal reasoning. So temporal reasoning is the ability to interpret and manipulate time-related information. In modern natural language processing, many tasks need this ability, such as QA, question answering, event prediction, and RAG, retrieval augmented generation. All of these can involve time-related information. And recently, a lot of benchmarks have been proposed to evaluate temporal reasoning, like TRAN and TimeBench. But even state-of-the-art models today still tend to get lost in long temporal sequences. They kind of forgot who they are, where they are, and what they are doing. Of course, people have proposed many ways to help models find themselves back again. So first, there's a lot, three main ways. The first is prompting engineering. So it's basically about finding the magic incantation that makes the model behave. And the second one is supervised fine tuning, like stuffing the model with a lot of temporal reasoning examples. And another line of work that is actually the inspiration to the author of today's paper. It's called test time scaling, and test time scaling roughly means we extend the model's reasoning process and keep gently persuading it to continue reasoning and self-reflecting until we hit a specific token budget. And self-reflection here means looking back at the reasoning so far and checking whether it makes sense, then refining the chain of thought until we either hit the token limit or the model is confident in its answer. Building on this idea, the authors propose a framework called TISER, Temporal Self-Reflective Prompting. I don't know why it's called TISER, but yeah. TISER aims to improve temporal reasoning accuracy while also improving traceability. So we can better see how the model arrive at the answer. How do they do that? So TISER has three main components. The first is prompting, second is data construction, and third is fine-tuning. So let's start with prompting. You probably all know what chain of thought is, right? Chain of thought prompting. In short, we ask large language models to think step by step, explicitly produce a reasoning chain, and then generate a final answer. Even a simple step by step introduction already gives a big boost in reasoning performance compared to standard just answer directly prompt. The author extend this idea and ask large language models to explicitly decompose temporal reasoning into multiple stages. The stages are reasoning, timeline construction, reflection, and final answer. So first, reasoning. This part is similar to standard chain of thought. Given a question Q and temporal context C, the model is asked to produce a preliminary reasoning trace R, and then cons timeline construction. Just like in your Lost Wallace story, you reconstruct what happened in order. You recall when you got on the train, when you walk into the restaurant, etc. Here, the model identifies main temporal events from the reasoning trace R and the context C, then it organizes them into a timeline T. Building this timeline not only helps locate key clues, like where your wallet might be, but also helps the model better understand the sequence and interdependencies of temporal events. Next is reflection. This is like when you step outside your door and suddenly think, oh, wait, is the money I brought enough? If it's not, you go back home. Then you step out again, notice that it's starting to rain, and go back again to grab an umbrella. Similarly, the model now looks at the reasoning traces R and the reconstructed timeline T and perform reflection. This is the chance to find and fix inconsistencies, omissions, or ambiguities. Finally, after repeated refinements and reflection, the model produces the final answer. In all of their experiments, whether with closed large language models, open large language models, or fine-tuned open LLMs, they use this teaser prompting strategy. So, reasoning, timeline, reflection, answer. Again. Now let's move on to data construction. To make sure model can really show test time scaling behavior, the authors extend three existing temporal reasoning datasets: TGQA, Temp Reason, and Time QA. Each sample in these datasets originally contains a question, a temporal context, and a gold standard answer. The author apply the teaser prompt to off-the-shelf LLMs, GPT-4o and DeepSeek. They ask them to generate intermediate reasoning traces. Each reasoning traces consists of a reasoning sequence R, an ordered timeline of events T, and a reflective verification F. They then let these off-the-shelf LLMs read their own reasoning traces and produce an answer. To ensure data quality, they only keep those augmented sample where the generated answer matches the original gold answer. In other words, only correct traces are kept. The result in the teaser dataset made up of filtered subset of TGQA, temp reason, and timeline. Once they have this high quality dataset, we can move to fine-tuning. They use low-rank adaptation, LoRA, that's supervised fine-tuning, to opened language models. One is Mistral 7 billion, another one is Xianwen 2.57 billion. After fine-tuning, the models are more stable at producing outputs in a structured format like this, like you just see, with reasoning, timeline, reflection, and answer. And there are also some experimental details, so we will talk about it in setup next. So here's the experimental setup, and it has three parts: datasets, metrics, and models. So first, it's datasets. For training, as mentioned, they construct the teaser dataset by filtering and argumenting three existing temporal reasoning benchmarks, and these datasets already have standard train and test splits. So the authors use the original train splits for argumentation and filtering, and then for supervised fine tuning, and then you use the original test splits for evaluation. For evaluation, besides the three in-domain subset of teaser, they also read two additional datasets as an out-of-distribution (OOD) tasks, TOT benchmarks. It's a more symbolic, abstract temporal reasoning, and another one is multi-hop RAG. So it's a multi-hop retrieval plus QA task. The idea is that for in-domain, they test whether teaser actually helps on similar temporal QA tasks. For OOD, they see whether the teaser framework transfer to a more symbolic reasoning and to RAG style tasks. And next is metrics. For metrics, they use two standard ones. The first is exact match. It's just like its literal meaning. Check whether the model's answer string matches the gold answer string exactly. And this is very strict, and it's pretty common in QA tasks. Another one is token level F1. They split the answer into tokens, they compute precision and recall, and then they compute F1. And this is more tolerant, even if the model doesn't match like character by character exactly, it can still get credits for partially correct content. So to put it simply, exact match judges did the model get it exactly right, and F1 judges if it's not perfect. Did it at least capture the key content? For temporal reasoning task, often one wrong year makes the whole answer wrong, so it's important to look at both precision and token level alignment, not exact match alone. And finally, the models. They mainly compare closed and open LLMs. So for closed LLMs, it's GPT-4o as a strong closed source baseline. And for open LLMs, they use Mistral 7 billion and Chongwen 2.57 billion. As I mentioned, they use this both for supervised learning, fine-tuning, supervised fine-tuning. On these models, they compare several settings. So one is that is standard prompting. So just using the original data set prompts without any special reasoning or timeline structure. And this is for the baseline. And the second one is only teaser prompting. So it's like prompting engineering. Use the multi-stage prompt with structure, reasoning, timeline, reflection, answer. And this test whether prompting alone can improve off-the-shelf models. And the final one is teaser with fine-tuning. So they use LoRa to fine-tune Mistral and Chongwen 2.5. Training data is the teaser augmented data set. They implement this with Hugging Face transformer on 8 A100 NVIDIA GPUs. During data construction, they also compare GPT-4o versus DeepSeek v2.5 as a teacher models for generating self-reflexive traces. And in that case, actually GPT-4o has done better. And this will matter later in the results. So next is in-domain results. So let's look at the in-domain result. Let's look at this table. The three benchmarks are TGQA, Temp Reason with L2 and L3, Time QA with easy and hard splits, and the role are different models and configurations. We can note a few things. So first, closed models, GPT-4o only, comparing standard prompting and teaser prompting. So micro macro exact match, so it's like average over all test splits, goes from 78.5 to 81.8. So even for a strong general purpose model like GPT-4o, just adding a teaser style reasoning, timeline reflection answer list with this prompting engineering gives a noticeable performance gain. For open models, Mistral 7 billion and Changwen 2.57 billion. For Changwen 2.5, teaser prompting actually improves performance on most test splits compared to standard prompting. Interestingly, on time QA hard, it improves, but the relative easier time QA easy split, it's actually the only one that gets slightly worse. For Mistral 7 billion, the effect is less stable. So like some data set improves with teaser prompting, others actually drop a bit. So this actually reflects what the authors say. These open-based models weren't originally trained to strictly follow this kind of self-reflection pipeline. So changing the prompt at inference time alone doesn't guarantee that they fully benefit from the framework. So let's see the fine-tuned, open LLMs fine-tuned, training data using standard prompting. To compare fairly with their own teaser dataset, author also fine-tune models using the original data formats. So that means without teaser traces, compared to the off-the-shelf models, these fine-tuned models do improve, but the gain is limited, and still lag behind the full teaser framework. So here comes the real highlight of all the full combination of teaser framework. So teaser data fine-tuning and teaser inference. And look at the roles fine-tuned with teaser training dataset generated by DeepSeek and teaser training data generated by GPT-4. With Changwen 2.57 billion using teaser dataset generated by GPT-4 and teaser prompting at inference, their result beat the previous TGQA's state-of-the-art model, TGLM, and also outperforms GPT-4o with teaser prompting. Even the weaker open models, Mistral 7 billion, after teaser-style fine-tuning and inference, it managed to surpass other configuration. Of course, except for Changwen 2.5, in macro exact match and F1 score. So this means teaser prompting alone gives a modest boost, but with full framework of teaser, with teaser style high quality training data and teaser inference prompting, can unlock the latent temporal reasoning ability of small open models to the point where they beat GPT-4o and prior state-of-the-art on these benchmarks. So next, table 2 answers the question, should we merge TGQA, Temp Reason, and TIQA into one larger joint training data set, or should we train on them separately? Here, they fix the model to Changwen 2.5 with teaser prompting and compare different fine-tuning settings. So train only on TGQA, train only on Temp Reason L2 or L3, train only on Temp TimeQA Easy or TimeQA Hard, or with full teaser dataset. So train on all of them together. Each resulting model is then evaluated on all benchmarks, and they compute the macro exact match across them. And what do we see? Each subset only model tends to perform best on its own test splits. This is as expected. The format and style are very similar between train and tests within each subset. But when these subsets only models are evaluated on other datasets, the performance drops. And their macro exact match is only around the 70s. In contrast, joint training on all teaser subsets does not cause them to drag each other down. In fact, it makes the model perform well across all datasets. So the conclusion is joint training with multiple temporal reasoning datasets under TISER leads to a more general temporal reasoning abilities, rather than overfitting to just one dataset style. So lastly, let's briefly look at the OOD downstream tasks, TOT benchmarks. So it's about general or symbolic temporal reasoning. So they involve step-by-step reasoning and symbolic operations, not just temporal QA. And authors found that TISER trained Chainwind 2.5 also shows significant gains on TOT, sometimes approaching or even surpassing larger closed models. Conceptually, this is important. Although TISER was designed for temporal reasoning, its core ideas, self-reflection and timeline construction, seem to transfer to more general multi-step reasoning tasks as well. And also multi-hop RIG. So we have table 3 evaluating a multi-hop RIG, a board domain multi-hop retrieval plus QA benchmark. And they considered 3 question types: inference, comparison, temporal. And the results, in short, GPT-4o is still strong overall, achieving the highest X match on inference, comparison, and temporal questions. But among the open models, though those that underwent teaser fine-tuning consistently outperforms their pre-fine-tuning versions, not only on temporal questions, but also on inference and comparison. So specializing the model using TISER for temporal reasoning does not destroy its other skills. Instead, it often improves them. Let's look at the ablation study. Which stage matters the most? We have been talking about TISER's 3 key stages: reasoning, timeline, reflection. Which of these stages actually contributes the most? The authors run an ablation study with configuration that keeps only one stage, and configurations that remove one stage from the full pipeline. So if you keep any of the intermediate teaser stages, you already get some benefits, as you can see. Whether it's only reasoning or only timeline, well, you might ask, why there's no only reflection setup? Because reflections, if you want to do reflections, you first need something to reflect on. There's no timeline, there's no reasoning. What you gonna reflect? So removing one stage from full teaser. So when they start from the full teaser pipeline and remove exactly one stage, the results show that reflection. We just mentioned reflection is the most critical part among know something configurations. Removing reflection hurts the performance the most, and this is actually quite intuitive, right? Because reasoning and timeline only helps think through the problem and organize events in timely order, but the reflection plays a role that catches mistakes and fixes logic. So without the final self-check, the model is much more likely to make detailed errors. For example, getting an error wrong or confusing order of events, and there's no check mechanism for that. Double check mechanism. Compared to all the other combination, only the full teaser pipeline consistently lifts open large language models reasoning, temporal reasoning ability to state-of-the-art levels. And also, the authors explains that why reason first, then timeline. The ablation also examines the ordering of stages. The author didn't choose directly build a timeline from question and context. Instead, they deliberately put timeline after an initial reasoning process. And here's their rationale. The first reasoning pass allows the model to scan the context and identify which events are actually relevant to the question and how entities refer to each other. And then, when constructing the timeline, it can focus on those relevant temporal events, producing a timeline that is coherent with the question. This matters because temporal contexts often contain a lot of irrelevant information. And if you build a timeline directly from the role context, you might include many unimportant events which adds noise. Authors conclude that the ordering, initial reasoning, timeline construction, self-reflection works better than other ordering and yields the most stable performance on temporal inference tasks. Okay, finally, let's go to the conclusion. The contribution of this paper is by designing a structured self-reflection pipeline and matching it with appropriate training data. There's a chance that small open source large language models can outperform even GPT-4o on complex temporal reasoning tasks. So yeah. And also through the TISER framework, temporal reasoning is decomposed into a reasoning, timeline, reflection, answer. They use GPT-4o and DeepSeek v2.5 to generate tens of thousands of such structured traces, and only keep those with correct final answer as high-quality training data with multi-data joint training. The model learns a general temporal reasoning ability that also transfer to broader reasoning tasks beyond pure temporal QA. But there's always a limitation. Yeah. So back to our lost wallet story. You finally use teaser style fine-tuning and prompting on GPT-4o, and the model successfully helps you figure out where your wallet is. Oh, finally you got your wallet. That's nice. You are thrilled until you look at the token usage. Yes, there's always a price for everything. It's very expensive. Yes. The biggest limitation of this teaser framework is the inherent cost of test time stealing, a huge token overhead. In large-scale deployments or RAG systems, at least computational cost is a serious concern. Yes, as you can see, the robots just take your money away. And the authors also note that in some other reasoning domains, it may not be straightforward to construct a similar reasoning traces. Even within temporal reasoning, they only consider text-only settings. So extending teaser to multi-modal temporal reasoning is left for future work. Yes. So that's everything for me. Thanks for listening. So I'm happy to take your question now.